Okay, so in this example, we've got to determine the magnitude of the force F for which the resultant moment and force for the system is 0. Okay, so let's just take a minute here and just evaluate what we're looking at here. So we've got a couple F. Okay, so we've got the force F, this guy here and this guy here. And so those are two forces. F and F indicates they have equal magnitude. They're parallel lines of action indicated by the angles of orientation here and here, and they point in opposite directions, so they form a couple. We have another couple, this 100 Newton force here and this 100 Newton force up here, they form a couple as well, because again, note the angles are indicating that they're parallel. They have equal magnitude and again, opposite direction. Okay, so we have two couples, and then we have three independent moments, right? So we've got the 150 here, the 250 at the origin here, and then the 180 down here. So what we got to do is we got to work out what is the value of the force F that is going to set the entire sum of the moments equal to 0. We can kind of see that baked into the question, the sum of the forces is going to be equal to 0. The sum of the forces already here is equal to 0 because we note that this 100 Newton force up here is going to be balanced by this 100 Newtons down here. And this F is going to be balanced by this F here. And of course, the moments have no contribution to the sum of the forces. And so by design within this question, the sum of the forces is actually already 0 because it's just made up of moments and couples. So there's no resultant force effect. What we have to do is work out really what's the value of F that makes the sum of the moments also equal to 0. All right, let's start off by working out what is the moment effect of the one couple here that we actually do have a force magnitude for, this 100 Newton force. So let's come on down here and break up this 100 Newton force, right? So let's sketch it out first of all. We have this guy here, which is 100 newtons. We have the fact that it's orientated at an angle of 40 degrees to the positive x-axis, something like this, and we can draw on a couple of force components as well. So we've got that guy, and we've got that guy. So the objective here is to work out what is the moment effect of this guy here and this guy here. Now, there's two different ways of doing this, right? We could work out, I could take the line of action of this force and extend it up that way, and I could take the line of action of this guy and I could extend it down there, and they're parallel. So I could, in theory, I could work out what is that lever arm there, let's call it Z, and I could take 100 newtons, multiply it by Z, and I'd end up with the moment effect. Instead of doing that, I'm going to just treat them as if they were two independent forces. I'm going to treat them as if they weren't a couple. So I'm just going to work out what's the moment effect of this guy and what's the moment effect of this guy here, and just add them together. It's the exact same thing. All right, so what have we got here? In the horizontal case, we're going to have 100 times the cosine of 40, which is going to give me 76.6. For the vertical component, it's 100 times the sine of 40, which is going to be 64.3. All right then, so let's just work out the moment effect, right? So we're dealing with this guy here first of all, right? So this guy here. So the horizontal component is going to generate a clockwise moment, and the vertical component is going to generate an anti-clockwise moment about the origin. Okay, so again, horizontal component generating clockwise about the origin, vertical component generating counterclockwise rotation about the origin. So with all that said, we can say that our horizontal component, 76.6 times a lever arm of 6 meters, that generates a clockwise moment, so it's positive. And then the vertical component generates a counterclockwise moment, so it's negative. So 64.3 times its lever arm of 13 is going to give me a negative 376.3. Now I can do the exact same computation for this guy down here, and it ends up being the exact same thing, right? So that in that case, the vertical component is again generating counterclockwise rotation, and the horizontal component is generating about the origin clockwise rotation. Okay, so we end up with pretty much the exact same thing. All right, and so the combined influence of both of those forces is going to be the two things added together, right? So another way of saying that is the total moment generated by that couple is equal to a negative 753.2 Newton meters. Okay, next we have to add, we have to work out what is the sum of the moments, right? So the sum of the directly applied moments. So let's go back up here. So that's going to be this 250, this 150, and this 150 down here, right? So the 250 is negative counterclockwise. The 150 in the top right is clockwise, and so it'll be positive. And then, let me see, this down here isn't actually 150. This is actually 50 Newton meters. Okay. And it's a positive 50 because it's clockwise. So we'll say the sum of the moments is going to be, the directly applied moments that is going to be 150 plus 50, negative 250 is going to give me a negative 50 Newton meters. Right, so what have I got? I've got a negative 50 is the sum of all of the directly applied moments. The other couple in the system has an influence of minus 753, and we're trying to balance that. We're trying to balance that with the couple generated by the two forces F and F here, right? So in other words, what we could say is the total moment to be generated by my couple is going to be the opposite of this plus this. So you add those together, you're going to get 803.2 Newton meters. So it's a positive 803.2 Newton meters that we have to generate. At that point, it's just a matter of working out an expression for the moment generated by one of these guys, and then solving for F, timesing it by 2 because we've got two forces, and then solving for F. Right, so let's have a think about this. We'll concentrate on the version or the force in the top left-hand corner, right? So we'll say that looked something like that. So what have we got then? We've got this guy is F times the cosine of 20. This guy is F times the sine of 20. And so the moment, the combined moment, is equal to F times the cosine of 20, right? That's just the force magnitude, times its lever arm of 10, negative or minus F times the sine of 20 times the lever arm of 5, right? So you've got that minus that, and you evaluate that and you end up with 7.7 F. Okay, so that's a moment, right? So that's the moment. Let's just call that MA, right? Now, we also have the moment generated by this guy down here, right? So that's going to be obviously the exact same thing. So we'll call that MB, and that's equal to 7.7 F. So what we're doing is we're saying 2 times 7.7 F is equal to, or must be equal to, 803.2. Okay, and we just solve for F. And so F is equal to 52.2 newtons. So that is the value of F we would have to apply at those locations and orientations in order to make the combined influence of all of these forces and moments, the combined moment influence, equal to 0. All right, and that wraps up that one.